بسم الله الرحمن الرحيم. Hello everyone. في هذا الدرس سأتكلم عن overcurrent protection of distribution circuits, and the reference is two books actually. Fundamental of Electric Power Quality by Santoso, and also Electric Power System Quality by Dogan, Professor Dogan. So the first thing I'll discuss about is overcurrent protection of distribution circuits, the devices that is being used to protect the distribution system in the power system. So we have a case when a short circuit condition exists in the power system circuits. Overcurrent protective devices must operate to interrupt the short circuit current at the minimum time required by the system. So these overcurrent devices includes fuses, automatic reclosers, sectionalizers, feeder circuit breakers. So we have four main things to protect the distribution circuits by overcurrent devices, and we must coordinate between all these four devices, meaning that I will go into depth into how to coordinate and calculate the time to coordinate between these four devices. We have the fuses. The fuses is a device that will have like a metallic thing or some materials inside a container, and it will melt to make like an open circuit to isolate the faulted system from the rest of the system, and it can only be replaced. It can only operate once and then you have to replace it. Whereas automatic reclosers are used to protect the fuse, because in the distribution circuits we have two types of fault. We have permanent fault, which is a fault that when it occurs it will remain there until the faulted part of the system is isolated by the circuit breakers or fuses. Whereas we have like a temporary faults. The temporary faults are usually self-clearing fault. For example, if a snake comes across the two feeders and then it will start to make a line-to-line fault, the snake will burn and then evaporate in few seconds, and then the fault is self-cleared because the reason for the fault is not there anymore. Or for example, a tree branch came across three lines, so we'll have like a three-phase fault, and then it will burn for a few seconds and the fault is self-cleared. So we don't want the fuse to act during the temporary fault. We want the recloser, which is actually a circuit breaker, which is open and close in a predetermined time, for example 3 times, and between each time there is a delay time, and this delay between each operation of the recloser is used for the protection of the fuse for the temporary faults. Sectionalizers are used with the reclosers to count the amounts of how many times the reclosers open and close. And the circuit breaker is actually a device that it's a switch that will protect the system during short circuit current, and can handle short circuit current, and also can handle maximum load current. So now this is an example for a typical distribution circuits with its equipment. We will have for example, the 138 kV transmission line, and then we will have two step down transformers on these two buses. We have the 138 kV bus and then 13.8 kV bus. These two transformers will step down the voltage. Here is the circuit breakers, two circuit breakers, and here is the tie switch, which is actually a circuit breaker as well. Then we have another tie switch here, and we have now for each feeder there is a circuit breaker. So this is the primary feeder, distribution feeder, and then we will have lateral coming out of this feeder. So each feeder will have a three-phase sectionalizers with the recloser, and then we will have a fuse on each lateral, and then a transformer to step the voltage down further. Then we might have a three-phase recloser here, and then three-phase sectionalizer here, and so on. The system can be complicated more than that, but this is a brief thing. Now for a radial system, this is called radial distribution system. Now the question is, which system has the better protection scheme? So I will assume that I'm having a fault right here. Which circuit breaker will open? Obviously this one. And if this one fails to open, this one will open after a predetermined delayed time. So if this one open and the fault was on this feeder, all the loads connected to this feeder will also be affected. And actually the fault wasn't on this feeder, but on the main feeder here. So the reliability will go down, since even the unfaulted system is disconnected due to a fault in somewhere else. What about this one? If a fault happened here or here, this breaker will open and the rest of the system will operate normally. What about if a fault happened here or here on the main bus bar? This breaker will open, so all this system will be affected, disconnected from the power supply. However, this load will not be affected by the fault. So this system number 2 is more reliable than system number 1. So even though we are using the same number of circuit breakers, selecting the position of the circuit breaker on the system is very critical, because in this way you can make the system more reliable, and it will benefits the power utility company for this reason. So for current interruption devices, for the circuit breaker according to IEEE standard number 100, it's a switching device capable of making, carrying and breaking currents under either normal circuit condition or abnormal circuit condition, such as short circuit. So making, meaning that has the capacity, making a capacity of the circuit breaker is the maximum peak current of the breaker that can conduct at the instant of closing, including the NEDC component. breaking is the breaking capacity of the circuit breaker refers to the maximum current in RMS value. So this is in peak value and this is in RMS value. So the other disconnect switches is not the same as circuit breaker. They can only handle the maximum load current, but they are not capable of interrupting fault currents. For the fuses, it's also overcurrent protective device with a circuit opening fusible part that is heated and severed by the passage of the overcurrent through it, so it only can be used once, while the circuit breaker can be used for multiple time. Now for the sectionalizers, it is used to coordinate the overcurrent protective devices such as the fuse, the reclosers, the circuit breakers. Doesn't have a relay and does not interrupt short circuit current, and used in conjunction with a recloser, as I mentioned, by counting the number of reclosing operation, and when count reaches a predetermined number, the sectionalizers trips and isolates the section through using the circuit breaker. Now for what is important for us is the characteristics of the fuse. Expulsion type fuse has a current time characteristics shown in this figure. So we have on the x-axis the current and on the y-axis is the time in seconds, and this is a log scale. So this is the area at which the fuse will start melting. So this is the line here is the time at which the fuse start melting, the minimum melting time, and this is the maximum clearing time when the fuse melt and open the circuit. So it's an inverse time current characteristics. This is an example. For example, the minimum melting time during, for example, 1000 amps. So during 1000 amp, the minimum melting time is something like 0.3, and the maximum melting time is something like 0.32 or so. And if we have like 4.35 kiloamps, then the minimum melting time is here 0.013, while the maximum melting time is 0.03. So there is a huge difference between them, something like 17 microsecond. An example for the fuse operation is find the minimum melt and total clearing times for the following currents. If we have an 80 amp faulted current, then we will look at the currents on the x-axis. This is 80, so we will go up until we reach here. So this will gives us 9.5 seconds. This is the minimum melting time. The total clearing time at which the fault is cleared is the higher value, which is here, and it is like 18 seconds, so it's like the double time. For a 200 ampere, the time will be much less because it's an inverse relationship. So in a 200 the minimum melting time is 0.95 seconds, and the total clearing time is 1.2 seconds. For 1000 amp, the minimum melting time is 0.035 seconds, and the total clearing time is 0.6 seconds. Now let's start talking about the reclosers. It's a circuit breaker actually, with a special use in distribution system to perform fault interruption and reclosing function, meaning that it will have, for a certain fault, it will have like 3 operation, like first open and then close, open and close, and then open for a permanent fault. Then it's generally used in overhead lines, as faults mostly are of temporary nature, so this is why they used it. Majority of the faults will be cleared in the first operation. Generally they are pole mounted, they have different design, either oil insulated or SF6 gas type, or sometimes it's vacuum circuit breakers. So this is a picture for the oil insulated recloser. This is for 3-phase oil insulated reclosers. So this is where the line will enter. This is an insulator. Then the line will come out from this bushing, and it's for 3-phase. This is with vacuum interrupters. There is a vacuum inside to distinguish the arc. So what is important about recloser is the time current characteristics. As for the fuse, we have like an area where we can find the minimum melting time and the clearing time. For reclosers, for each reclosers, we have 2 curves. One is the fast curve, which is here down, and the other is the delayed curve. So we can start, for example, from the fast curve for the first 2 operation, and then we will start a delayed curve when the fault is permanent, so that the fuse curve will be in between the 2 curves, so the fuse will melt down to clear the fault. Then the recloser will close, so that the rest of the system will regain surface. I hope this is clear. This is a typical distribution system. There are 2 most common sequence in use on 4-shot reclosers. It's called midline or tab. We might have 1 fast and 3 delayed operation. We might have 2 fast and then 2 delayed operation. So this is the recloser. This is lateral number 1, 2, 3, and 4, and each lateral has a fuse. So if there is a fault on this tab, on this lateral for example, then the recloser will open. Let's say we are using 1 fast and 3 delayed. This is the normal voltage, this is the faulted current. The recloser, which is a circuit breaker, will open for a few milliseconds, or for a second for example, or few seconds, and then it will close again. So still there is a fault current due to the fault on this lateral. Then the recloser will open, then it will close again, then it will open, then it will close again, and then it will open, and finally it will close again permanently until this fuse is blow out, and then the faulted part of the system is removed by the fuse. Then the recloser will close again to give the service to the other unfaulted customers. For 2 fast 2 delay, we will have one fast operation, and then the recloser will open, then another fast operation, then the recloser will open, and then a delayed operation, and the fuse will either melt here in this delayed operation or in this delayed operation according to the design. And this is how it works out. The circuit breaker usually of the recloser operates using a breaker trip coil. So we will have on each line a current transformer, and the current transformer has like a pickup current, and then if the current that is transformed by the current transformer, if it's larger than the pickup current, then this relay coil will energized in such a way that it will close this normally open contact, and when the normally open contact close, the battery will inject the current in the breaker trip coil, so the breaker trip coil will open the breaker contacts, and this is how circuit breaker operates. If the current on the secondary side of the current transformer is less than the pickup current, the relay contacts remain open. So to ensure that during normal operation, even at maximum load, the breaker will not trip in this normal operation. It will only trip during abnormal conditions. So what they did is that they provided a time delay over current relay, meaning that when a fault occurs on the system, it depends on the magnitude of the faulted current how much time the breaker should operate, meaning that if the current on the secondary side of the current transformer is much greater than the pickup current, then the relay operates instantaneously. And if the current of the secondary transformer is greater than the pickup current, but it's not, its magnitude is like 3 times or 2 times the full load current, then the relay will operate with like a longer time. So this characteristic is known as time delay over current relay. So we will have 2 things. We have a current tap setting and a time dial setting. The current tap setting pick up currents in amperes, adjusting the pickup current of the relay, and the time delay setting is adjusting the amount of time to delay the operation of the relay. So this is a typical type like electromechanical time delay over current relay by ABB Westinghouse. We have like a current tap setting in ampere, and it's between 0.5 up to 12, and then we have the time dial setting, which is the curve between the relay input current in multiples of the current tap setting here, with the relationship with the relay operating time in seconds. And this is like typical time curves for like a C08 type. There is a C06 and other types of the same thing. Okay. This is an example. We have a C08 relay with a current tap setting of 6 amps and time dial setting of 1 amp. So let's say we have a current on the secondary side of the current transformer of 5 amps. So since this is a 5 amp, which is less than the pickup current, so the C08 relay does not operate. While for a current of 8 amps, and why it does not operate? Actually, if we divide 5 divided by 6, so we divide I dash by the current tap setting, which is 6, I will get something less than 1. And since I will get something less than 1, this region from 1 up to 2, the relay will not operate. If I get something like between 1 and 2, the circuit breaker will not operate, and its operation depends on the time dial setting. From 1 to 1.5 here, it will not operate if the time dial setting 0.1, but it will operate if the time dial setting is 1 here. So let's see here. 8 divided by 6, the pickup current is 1.33. So the related operating time, let's say this is 1, this is 1.5, so 1.33 is around here, and the time dial setting is 1, so we are looking at this curve, so I will get something around 6. And if the I dash is 15 amp, so 15 divided by 6, I will get a pickup current of 2.5. So let's go to 2.5. This is 2.5. I'm going to this curve, which is 1. I will get something around 1.2 here, or 1.1, something around this time. So how to find the pickup current? We divide I dash dividing by the current tap setting. Then after finding the pickup current, we look at this. The pickup current is actually the input current in multiples of the current tap setting, and then we look at the time dial setting. We adjust on the relay to get the time operation of the relay.